fluid mechanics, we are going to continue with forces on submerged surfaces in static fluids. So this topic falls under static fluids. We are still looking at static fluids. So this is the last chapter that we are going to look at, which is forces on submerged surfaces in static fluids. So far we've seen that whatever force that acts on static fluids is supposed to be acting perpendicular to the surface and at right angle to the boundary. And the other thing that we have learned also is, when you look at Pascal's law, is pressure at any point acts equally in all directions. This is only possible and true for a continuous fluid that we'll be looking at. So if you remember last time, we talked about fluids, forces acting perpendicular or acting in all direction, equally in all direction for a fluid that is continuous. If we take maybe a force where there is mercury and the other side there is water, even if the force is acting perpendicular, we are not going to get the same pressure at that point. So what we have to put in mind is pressure at a point acts equally in all directions, and this is supposed to be for a continuous fluid. So the other thing that we have looked at again, it is fluid pressure on a surface. We know that when you're looking for fluid pressure, pressure is equal to force per unit area. So in other words, pressure will be equal to force per unit area, and force will be equal to pressure multiplied by the area that we have. And since the fluid is at rest, the force that we are going to calculate will be acting at right angles to the fluid. So these are the basics of static fluids that we need to put in mind every time. That whatever we are going to calculate has to be based on these facts that we have and theorems that we have, from Pascal's law to hydrostatic laws and all the things that we have looked at before. So now for submerged fluids, if we look at this horizontal plane and we assume that it has been submerged in water, we see that the force is going to act perpendicular to the plane that we have submerged in water. It's submerged at an angle here, so which means force 1 is equal to pressure at 1 multiplied by the area at that point 1. Force is 2, pressure at 2 multiplied by that area, and force at n is equal to pressure at n multiplied by the area at n at that particular point. So now if you want to find the total resultant force for this plane that has been submerged in water, we are going to sum all the elements that we have. So which means this R is going to be pressure at 1 multiplied by area at 1 plus pressure at 2 multiplied by area at 2 plus all the elements that you are going to look at this horizontal plane. So in other words, we can just write R is equal to summation of pressure multiplied by the change in area at this point. So this one is going to be one of the general formula that we are going to use to calculate the pressure at this point, or the resulting force at this submerged plane that we have here. So if we look at hydrostatic law, we know that pressure increases with depth. So pressure is going to increase with depth. So in this case, we are not going to get equal pressure for a submerged plane like this. So which means we are going to get less pressure force here close to the surface, and more pressure force close at the bottom of the where we submerged the plane towards the bottom. You are going to get the highest pressure. So which means if you are going to get our center of pressure is going to be located towards this point near the bottom. So it's like if you are on a seesaw, you know that if you've got higher force here on a seesaw, if you've got higher force here, for you to balance the moments that you're going to get, which means this other side is supposed to be balanced by the length of the beam that we have. That's why we see here that we've got higher force that we are going to get at the bottom, due to the fact that pressure increases with the depth. So if pressure increases with the depth, we know that force is equal to pressure times area. So which means if we've got higher pressure here, we've got also higher force. So for us to balance now, or to find the center of pressure, or to balance this beam, we need to move our center of pressure towards the region where we have got higher force here, so that at the end of the day, this moment that we are going to get this other side towards the surface will be balanced by the length of the beam that we have. Okay, so what we are going to see here is what is known as the center of pressure. So center of pressure is defined as the point where the resultant force is going to act, the point at which the resultant force is acting. So now if we look at a horizontally submerged plane, if we've got this plane and is submerged horizontally, we know according to Pascal's law that the pressure that is going to act on this plane is going to be equal at any point, provided it's a continuous fluid. So if we use this formula that we have looked at as R is equal to summation of pressure multiplied by area. So what we are going to do now is to find the resulting force. We are just going to find the pressure at any given point and multiply by the area of the whole plane. Then we are going to get our R is equal to pressure times area. This is only possible for a horizontally submerged plane. Then when you are looking at curved submerged surfaces, we are going to find pressure at any given point of the submerged curved surface, and then use this formula, which is summation of pressure multiplied by delta A, to find the resulting force of acting at the curved surface. We'll come back to this part when we are going to look at some examples and also some of the formulas that we are going to use to solve problems that have got curved submerged surfaces. So from horizontal, if the beam or the bar that we have is horizontally submerged, this is straightforward. For you to find your resulting force is equal to R. R is equal to pressure multiplied by area, and the center of pressure will be at the center of that beam, since we are going to have equal pressure at the horizontal surface that we have. Okay, so let's come back now to a more complicated situation that we have here, when we have got a plane that is submerged at an angle like this. So we've got angle theta here, and from there, since it's submerged at an angle, we know that pressure is going to increase with depth. So here, as we reach this depth D, we are going to get higher pressure here compared to the pressure that we get at the surface. So we've got this distance, vertical distance that we have. We know that when you are using hydrostatic law, we say its pressure is equal to rho GH or rho GZ. Z, where Z is the perpendicular distance, is the head. We defined the head as the perpendicular distance that we want to calculate here. So if we look at this point, we've got pressure is equal to rho GZ. So pressure at this point will be given by rho, which is the density of the fluid that we have, multiplied by the acceleration due to gravity, and multiplied by Z, which is this perpendicular distance that we have. But since now it's at an angle, which means we need to use trigonometrical identities to find this Z that we have here. So for here, what we are going to look at is for us to find the force. Force, we know that is equal to pressure multiplied by change in area. So we are going to get rho GZ multiplied by change in area. Consequently, for us to find out the resulting force, we know resulting force is equal to the pressure or summation of the pressure multiplied by change in area. So if we substitute pressure by putting rho GZ here, we are going to get rho G outside the summation point, because we assume that we have got a continuous fluid. So rho is the same, density is the same, and acceleration due to gravity does not change. So we are going to get rho G summation of Z. Z is going to change, because Z at this point won't be equal to Z at this point, and won't be equal to Z at the last point here. So Z is inside the summing point that we have. So we have got rho G multiplied by the summation of Z multiplied by change in area. So if we look at this point that we have, or this notation that we have, summation of Z rho A, change in A, this point or this summation that we have, or this notation that we have, is known as the first moment of area. So if you are asked to calculate the first moment of area, you have to put in mind that we are calculating the summation of all the Z's that we are going to get here and multiply by the change in area. Or we can write it as simple as this: A multiplied by Z bar. Then this one gives us what is known as the moment, first moment of area. So from there, A is the area of the plane and Z bar is the distance to the center of gravity. Okay. Then if we are going to continue with this problem, so which means if we look at Z bar, which is here, which is at the center of pressure, Z bar, for us to find Z bar in terms of this distance, which is x, we will need now to use those sine, theta and cos relationships that we have. So in this case, we can take a note. We see that Z bar, we have got opposite and hypotenuse, and we've got our theta here. So if we've got opposite and hypotenuse, what we are going to use is Z bar will be replaced by X bar sine theta. So we've got our now first moment of area will be given by summation of Z delta A is equal to A X bar sine theta. So this becomes the notation that we can use from here. So for us now to calculate the resulting force on the plane, we can write R is equal to rho G A Z bar. Rho G A Z bar. So what we have done is we have replaced this summation of Z delta A. We have replaced it with A X bar sine theta. So we can write R is equal to rho G A X bar sine theta. That will be the resulting force that we are going to get at this point. So we will know that this resulting force will act at right angles through the center of pressure, which is C, at a depth D. So if you come back to this point, which means it will act at the center of pressure, which is C, at depth D. That's where we are going to get our resulting force. So someone can ask, like, why is our center of pressure down here or towards this end? We will know that at the end of the day, pressure increases with depth. So which means for us to have a more balanced moment here, we need this length to be longer than this other side, so that when we do summation of moments to get equal to 0, which means at this point the longer arm will compensate for the smaller force that we have this side, and here we've got larger force, so the larger force will compensate the shorter distance that we have from C to P. Okay, so what we can conclude now is the resulting force on a plane will be equal to density multiplied by gravity, acceleration due to gravity, multiplied by area, multiplied by X bar sine theta. Okay, so now how do we find this position, or how do we find the position at which the center of pressure is acting? So what we need to do now is to find the moments. We have to take the moments of the force. So if you are going to take the moments of force, we know that a moment of force is defined by moment of a force is equal to the force multiplied by the perpendicular distance. So here we've got the force, which is rho G Z multiplied by delta A, or we can write it as rho G S sine theta delta A. So if you come back to this diagram, our S is this distance from here to this point of G. That's where the S is that we have here, that we are looking at. So which means we are going to say rho G S sine theta multiplied by delta A. So for us now to calculate the moment, we have to calculate the moment as rho G S sine theta multiplied by delta A and multiplied by S. So which means the moment that you are going to get the moment of the force about O will be rho g sine theta delta A S squared. So we are looking at the moment of force about O, which is this point, about O. About O. Okay. So from there, we can get the sum of moments, which is equal to rho g sine theta summation of S squared delta A. So here we are assuming that it's continuous fluid, so we've got density, which is constant. Of course, acceleration due to gravity, we take it constant. And sine theta, we are not changing any angle, so this is constant. So the only thing that can vary is S and A. So from here now, the moment of R about O will be equal to R multiplied by SC, which will be rho g A x bar sine theta multiplied by SC. So our R here, we've already calculated R. R is the resulting force, which is rho g A x bar sine theta. Then we are looking at about O. So which means about O, we have to look at the center of pressure, which is SC. So we are looking at center of pressure, which is SC here at this point. So which means we need to calculate this distance, which is SC from O. Okay. So from that point now, we'll get our moment of R about O. So now equating the two, this moment of R about O and the moments and the summation of moments that we have, we'll get this equation, which is rho g A x bar sine theta SC, moment of R about O, should be equal to rho g sine theta summation of S squared delta A, which is sum of moments. So in this case now, what we are going to do is to find this SC, because that's the unknown that we are looking at. We are looking for SC. So when we equate all these equations that we have, we see that rho g cancels out. Sine theta cancels out. So what remains now is summation of S squared delta A divided by AX bar. So when you look at this equation that we have now, it's known as second moment of area. Second moment of area. And it can be written as I naught. So second moment of area about O, I naught, what you are looking at is summation of S squared delta A. So summation of S squared delta A is known as the second moment of area. So in other words, if you are going to look at the position of center of pressure along the plane measure from the point O, it can be written as SC is equal to second moment of area about a line through O divided by the first moment of area about a line through O. So like what we have seen before, this one is the second moment of area, and the down one or the bottom one is the first moment of area. So SC will be defined using this notation that we have. Second moment of area about line through O divided by first moment of area about line through O. Then now to calculate the depth of center of pressure, what we need to do is to use D is equal to SC sine theta. So if we come back to the diagram that we have, for us to find this depth, which means we've got SC, we've managed to find this SC. So for us to calculate now the depth, which is from the surface to the point at which the resulting force is acting, we've got angle theta here, so it's opposite over hypotenuse. Sine theta is what opposite by hypotenuse, so D over SC. So in other words, for us to find D, we can write D is equal to SC sine theta. Okay, that's how we will be able to find our depth to the center of pressure. Okay, so from there we will now need to use the parallel axis theorem to find the second moment of area. So the question is, how do you calculate the second moment of area? So we need to use the parallel axis theorem. So parallel axis theorem is written as I naught is equal to IGG plus A x bar squared. I naught is equal to IgG plus A x bar squared. So in other words, now for us to get the final equation that we need to use, we can substitute this in the previous equation, and we are going to get SC is equal to IgG over A x bar plus x bar. Then our D, which is the depth, will be equal to sine theta IgG over A x bar plus x bar. Please take note of this equation. We use it a lot when calculating and solving problems in this topic. So SC and D, you need to know and master how to use this. Of course, in the exam, the parallel axis theorem and the IgG will be given, so there's no need to memorize this part. I'll give you the IgG. Someone can ask, what is the IgG? IgG, there are different IgGs according to the shape that you are using. So which means second moment of area IgG about the axis through the centroid. If it's a rectangle, we use b d to the power 3 divided by 12. So which means I'll give you this table in an exam, so there's no need for you to memorize this part. So for example, a question can come like this: find the moment required to keep this triangular gate closed on a tank which holds water. So which means we've got a triangular gate that we have here and is submerged in water. Small, like a point whereby we've got a gate, maybe a bridge or a dam, where we've put a gate that sometimes we might need to open this gate to allow some water to come out for us to regulate the flow or the level of the water in the dam. So now there is some force that is going to be exerted at this gate. So maybe you might be asked to calculate the forces and the depth and all the like that is there. But knowing that the gate that we have is a triangular gate, so for us to use these equations to solve this problem, we will need to know the IgG. So what we need to do is to come and check in this table. Okay, what we are given here is a triangle. So if it's a triangle, the second moment of area IgG will be BD to the power 3 over 36. So that's what we need to use here. So we know that our B is this distance and our D is this distance that we have. Then we've got BD to the power 3 divided by 36. If it's a circle, pi r to the power 4 over 4. Okay, so put in mind this, and there's no need for you to memorize this table because it will be given in the exam. So for us to solve these problems, we can also use what is known as pressure diagram, but in this course we are going to skip this part for pressure diagrams. Because of time, we are not going to use much of pressure diagrams. So but during your spare time, just go through this. You will see that even if you use pressure diagrams, you are still going to find this answer: resulting force per unit is equal to Ri is equal to half rho gh squared. That's the answer that you are going to get. So if you are going to compare with what we have done, which is using the moment method, we need to find that Ri is equal to rho gax bar, which is equal to this part. And when we solve for a triangle, since here we are solving for this triangle that we have, we will know that at the end of the day, rho g is equal to h multiplied by 1 h over 2 sine theta. We'll still get the same answer, which is equal to this part. Okay, so but in this course, what we are going to use mostly is the moment method. So for pressure diagram, if you master it on your own, you can use it to answer the questions, but what we are going to use the most is moment method. Okay, so now to find our D is equal to sine theta I naught over A x bar. So I naught, we know I naught already. I naught is given by a IgG plus A x bar squared. Then from there we need to find our IgG depending on the shape that we are working with and substitute in this equation to get our depth. So for the depth, you are going to get D is equal to 2/3 H, which is the same answer that we got from the pressure diagram. D is equal to 2/3 of H. R is equal to half rho GH squared. We got the same answer here for R, and we are also getting the same answer here for D. So either method can work, but like what I said, we are going to use mostly moment method. That's what we are going to use. So also take note of this point, that if you've got different fluids that we have in a container, we are going to get a different approach here. So which means this curve that you are going to get for oil is different from the curve that you are going to get for water. But you have to put in mind that despite that we have got two different fluids, pressure will still increase with depth. So we are going to get higher pressure at the bottom of this tank, for example. Okay, so let's look at the last part, which is submerged curved surfaces. Like, how are we going to solve problems that have got curved surfaces? So for curved surfaces, what we need to do now is to solve the problem in two. First, we find the horizontal component, and then we find the vertical component. Then we use the equation for finding the resulting force, which is equal to square root of force in the horizontal squared plus force in the vertical squared. So which means square root of force in the horizontal squared plus force in the vertical squared for us to find the resulting force. Then from that resulting force, we also need to find theta, which is equal to arc tan force vertical over force horizontal. Okay, so now in this diagram that we are given here, we've got force that is acting at this point, which is a curved part. So maybe we've got water in a pipe, then we've reached a point where there is this sudden contraction that we have from a bigger pipe to a smaller pipe. So which means there's force that is going to be exerted here. So we need to first solve the force in the horizontal direction and also in the vertical direction. Then that's when we can find the resulting force that we are looking at in this case. So for the horizontal force, RH is equal to the resulting force on the projection of the curved surface onto a vertical plane. So that's what we are going to look at now. This is what we are going to work with, that the resulting force on the projection of the curved surface onto a vertical plane. So what we are going to do is to isolate this part. Instead of looking at this whole pipe, we are going just to isolate the curved part that we have and come up with a diagram like this. So which means we are going to get this force, RH, will be equal to the same force as F at AC. Okay. Then from here we know that the sum of horizontal forces is equal to 0. So the force, why is it equal to 0, is the fluid is at rest. It's a static fluid. So if it's a static fluid, which means summation of forces is equal to 0. So if summation of forces is equal to 0, in other words, what it means is the force in this direction, which is force at AC, should be equal to the force in the horizontal direction going the other opposite direction that we have here. So that when we add RH and FAC, we are going to get 0. Okay. So what do we know so far? We know that the force on a vertical plane must act horizontally. Then the other thing that we know is RH must act through the same point. Okay, so what it means is RH will act horizontal through the center of pressure of the projection of the curved surface into any vertical plane. Okay, so from there now we can calculate our RH at that point. Okay, so after getting RH, the next thing that we need to calculate is the vertical forces to find RV. So now, since there are no shear force on the vertical edges, so the vertical component can only be due to the weight of the fluid. So this RV that you are going to get will be as a result of the weight of this fluid inside here. So if it's as a result of the weight of the fluid, so which means RV will be equal to mg, mass times gravity. So mass times gravity, then, which means we are going to say RV is equal to the weight of fluid directly above the curved surface. Okay, so RV will be equal to weight of the fluid, so which means it's equal to mass times gravity. Okay, so it will act vertically through the center of the gravity of the mass of the fluid. Okay, so now that we have managed to find RH, we can calculate, and RV, we can calculate R, which is the resulting force. So resulting force will be equal to square root of R squared H plus RV squared. Then from there, like what I said, we will also need to find theta, which is arctan RV over RH. So this is a typical question that can come where we're asked to determine the forces on the dam walls or curved gates. So we are given this dimension, that the water, we have got water, so which means if it's water, our density will be 1000 kgs per meter cubic, and we have got this radius that we have, which is 1 meter, and the gate width is 3 meters. So which means what we need to do is to find the forces acting on this dam wall. So we'll use this equation that we have. First we need to find the RH, then we need to find the RV. From there we find R is equal to square root of RH squared plus RV squared. Then we find also the angle at which the resulting force is acting. Okay, so now if we've got the fluid below the curved surfaces, how are we going to solve the problem? Okay, the force calculation will be similar to what we have looked at for a curved surface, whereby we've got the fluid inside the curved surface. Now here we've got the fluid below. Last time we were looking at a scenario whereby the fluid was above the curved surface, but now in this case it's below. So if it's below, we'll still use the same procedure. We still need to calculate RH. RH will be calculated the same like the way we have done before. We need to find that for horizontal force, FAC should be equal to RH, so that we can get that resulting force which is equal to 0 in the horizontal surface. Then for the vertical one, what we are going to do is we are going to imagine that this fluid was above. So which means RV will be equal to the weight of the imaginary volume of fluid vertically above the curved surface. So what you just do is we imagine that this volume of fluid was above. So which means we still use the same formulas like before to calculate the resulting force. So after getting our RV and RH, we use this equation. R is equal to square root of R squared H plus RV squared, and theta is equal to arctan RV over RH. Okay, so let's just summarize everything that you have learned today from this diagram that we have here. So we know that point A and B, point A to B, this is a horizontally submerged bar that we have, or plane that we have. So if it's horizontally submerged, we know that according to Pascal's law, the force will act equally on this horizontal plane. Act equally. So if it's acting equally, what we are going to get is our resulting force will be equal to pressure. R is equal to pressure multiplied by A. And the center of pressure will be half the length of this plane that we have. So we are going to have equal distribution of pressure around this point AB. Now let's look at point BC. So we have assumed that we have submerged a plane vertically into water or into a fluid. So we know that pressure increases with depth. So which means that the pressure that you are going to find at point B will be less than the force that you are going to find at point C. So that's why we've got this one, which is a linear distribution of pressure, where it's increasing from point B to point C. So now our center of pressure is no longer at the center of this plane that we have. It's now biased towards the bottom, where we are going to get the highest pressure. Okay. Then when you look at a curved surface, so this one is a curved surface. So for a curved surface, which means we need to find the force for FH, vertical horizontal force, and the vertical force. Then from there we find the resulting force, which can be found using this formula, which is horizontal force plus vertical force under a square root, to find this FR. Okay. Then at the end of the day, we will need also to find angle theta, which is arctan FV over H. Okay. So this diagram that we have here summarizes everything that you have learned so far. So we've got horizontal projection, we've got vertical projection, and we've got curved projection. Those are the three scenarios that we'll find when we are working with forces on submerged surfaces in static fluids. Okay, so if you master these three, any question that will come your way will be easy and straightforward to answer. So the other scenario that we also looked at is when the fluid is below or outside the curved surface that we have, and we say that we still use the same approach as if the fluid was above or inside the curved surface that we have. Okay, so the next thing is just to look at tutorial questions which are below. So kindly answer these questions on your own. Then if you've got any challenges, please let me know. So question 1, answer question 1. Then here, answer question 3-143, this one. Then question 1.7, answer all those questions and please submit your answers as soon as possible. Thank you very much for your attention. See you next time.